Okay.
Our next speaker is Max Xu from Stanford. He speaks on a Turán conjecture and random multiplicative functions. So please.
Okay. Yeah, thank you for the introduction and thank you for organizing this nice conference. So today I will talk about a recent joint work with Rodrigo Angelo, who is also a PhD student at Stanford. And it's motivated by observation, let's say, by Turán and connected to object called random multiplicative functions. I will explain what do I mean here. So yeah, this is cool. So if you haven't met Rodrigo before. So I will first talking about this Turán's conjecture on logarithmic average of Liouville function. And then I will mention this object called random multiplicative functions. And then the second part, I will mention the main results of our paper. And then at the end, I will focus on how to prove the theorems. So the object we want to study actually, let's say Turán it was interesting, it's very simple. You just consider the partial sum of Liouville functions. So I just remind you, Liouville function is defined to be at primes to be -1, and they define all the positive integers completely multiplicatively. So like lambda 6 equal to -1 times -1 equals to 1. So we are interested in this partial sum weighted by 1 over n. So that's usually called logarithmic average. And you can compute this partial sum actually, for example, the very first several terms. So for example, the first term will be 1 basically, and second term will be lambda 2 over 2 will be -1/2. And then you can even consider the third one is -1/3. And interesting, if you sum them up, this first partial sum seems always positive. So at least if you just compute by hand, it seems very hard to find a negative sum. So it turns out there's a very brief conjecture that if you do believe that this partial sum Sx truncated at x is always positive. And what Turán did is the observation he had is like, if indeed like Sx is always positive, then this actually even can imply IH. So then we should, well, this, if you want to, we all know IH is very hard. So probably to prove Sx is always positive is very hard, or even it's not true. And indeed, Hasselgrove in 1958, he disproved that this Sx can be always positive. So basically, it must be negative at some point. And the next question you want to ask, maybe one is the first time this sum becomes negative. Can you find an explicit truncation such that this partial sum is negative? And of course, it's very hard to find it by hand. And it turns out this number is very huge. It's around like 10 to the 13 or something. So it's like this is the first integer such that this partial sum of weighted Liouville function is negative only appeared at like this n0. It's a huge number. So now this is basically the like very brief history about this problem. And now I want to move to the second topic, object I want to study. So it's called the random multiplicative functions. I just briefly mentioned the one model here. Is like if you take your fp to be a random variable, identical and independently taking value from 1 and -1 with equal probability half. And then similarly, you can define fn completely and multiplicatively. So it's like, for example, Liouville function, you can consider it as a sample of this f of random multiplicative function. Basically, take a -1 at all prime p's. So now the original Turán's conjecture was not correct. So it's like you cannot have the partial sum of Liouville function weighted by 1 over n cannot always be positive, but a similar more probabilistic question you can ask is like, now if I consider all random multiple function, the sampling of IMF, what's the chance that your partial sum is always positive for all x, no matter where you truncate, it's always positive. And first of all, the first observation is that it cannot be arbitrarily close to 1, because you can construct a lot of IMF, like a sampling of IMF, such that it will be negative at n0. The reason is just you match your f, you let f match a Liouville function for all primes up to n0, and then for all primes larger than n0, you just take whatever you want. So this gives you a proportion like 2 to the negative pi 0, pi n0. This amount of proportion of IMF, such that it will be, the partial sum will be negative at n0. So this gives you at most upper bound at most 1 minus this very small number, such that the probability that this IM always positive can only be at most this quantity. So it's strictly bounded away from 1. Now you might be wondering, like, if this chance is really close to 1, or maybe like a half, or negative, or 0.6 or something. And the result we proved is actually, although this one is strictly bounded away from 1, but actually can be very, very close to 1. So we prove that if let f be a sample of the IMF, the probability that this weighted partial sum is always positive is actually at least 1 minus a very tiny number, and this number is 10 to the negative 45. Okay, so it's like very close to 1, and it's bounded below, strictly bounded below from strictly bounded away from 1. So now I want to motivate another result is like, instead of considering being positive for all x, what if we just ask like, what's given a very, very large x? If I truncate a very large x, what's the probability that this partial sum truncated at a large x is positive? And the result we also can prove something on this line is like, this exceptional probability is roughly exp, negative exp log x divided by something times log x. So, and the previous results along this line actually in 2007, Granville and Sound proved that for each large x, you actually can always find or construct a complete multiple function such as a weighted average is negative at this specific x you are interested in. So this actually gives you an upper bound that this exceptional probability can be at most 1 minus 2 to the negative pi x. So of course, these two bounds don't match with each other. So this is the Granville and Sound prove more like up bound, and what we prove is like a lower bound. So this is two main results I want to discuss with you today. Now, I will mostly focus on proof of the first theorem, and that's actually the slightly more involved ones. And the proof of theorem 2 is basically follow the same strategy of first theorem. So we know that based on previous work, we know that for Liouville function lambda, the partial sum are always positive. Up to n0, a huge number is always positive. That's something we already know. And then the first proposition I want to discuss with you is like, actually not just for Liouville function, for any completely multiple function. If you're only taking value from 1 and a negative 1, then actually if you truncate up to n0, you're always being positive. So this proposition is really saying that as long as Liouville function is for Liouville function case is positive up to some point, then actually for all the other completed multifunction, you don't need to worry about them. It's all fine up to that n0. So the proof is very simple. So we construct a function g to be the directory convolution of f, and the absolute value of this function of Mobius function. I believe everyone knows is what is Mobius function. Basically, it's a multiplicative function, and it's a on prime power take to 0, and on primes take to -1, and for distinct primes to -1 to the number of prime factor you have. So and you can easily to see that g is non-negative. And then the key point now is for any function f, completed multifunction, the logarithmic average of fn, you can write it as because f now is the g convolution with lambda, so it can written as a product of some logarithmic average of g and logarithmic average of lambda. And now notice that g is non-negative, so this term actually is fine. We don't need to worry about it. And this term, because by our previous known result that this term is obviously positive, so the product will be positive, basically. So this is a sketch of the proof, which basically tells you that up to n0, this huge number, we don't need to worry about anything. So for any f, it will be fine. So the real problem is what about if your x is much bigger than n0? So remember, the theorem one we care about is like for truncation at all x. So for general large x, what we do is actually very simple, but the key decomposition. So we know that fn over n is multiplicative, and then first thing you come to your mind probably like, okay, you can factorize it as some Euler product. And indeed, you can more or less can factorize this sum of n over n by some product up to p up to x, like 1 minus fp over p is a very standard thing. But you have some small tail. This tail is like fn over m for some n even bit larger than x, but its largest prime factor. So here pn I denote for this largest prime factor of n. Like for those integer n, although it's larger than x, but is the largest prime factor is also smaller than x, then this term we need to throw them away. So basically, the quantity we're interested in is a very nice Euler product minus some tail we want to estimate. And the nice thing about this random Euler product is that although we know that the random multifunction itself somehow a lot of terms are dependent with each other. For example, f6 is dependent with the value of f2 and f3. But once you written them in terms of Euler product, we know that each factor now is independent. In particular, because all the fp, by the definition, all the fp taking value independently. So this product is really a product for independent random variables. So this quantity, we should have some confidence to understand them. And now, as long as we can show that this quantity, this tail contribution is negligible, then we should be fine. More or less, we want to show something like this random Euler product is reasonably large, like bounded away from 0, slight like towards positive. And then we also want to show that this tail actually contributes very, very small. Then we basically can say something. Okay, that's the general plan. So as I just mentioned, we first want to show that these random Euler products are reasonably large. So when I say large, actually, I just mean bigger than something like 0.1. So we show that this Euler product is, if you want it to be small for some x bigger than n0, actually it's very, very unlikely. It's 10 to the negative, for example, 45. So that's the first thing we want to show. And the second thing, as I mentioned, I want to show this tails actually is very, negligible. We want to show that this sampling, that would be a sample of the IMF. Actually, we want to show this tail bigger than 0.12. Actually, is also very negligible probability. Okay, based on these three propositions, we actually already finished the proof. Because proposition 1, that's telling us that for any x truncation smaller than n0, we don't need to worry about them at all. And proposition 2 and 3 take care of the rest case. Because as long as the x is bigger than n0, proposition 2 is basically telling us that the Euler product is always bigger than 0.12 up to some very tiny, small exceptional probability. And proposition 3 tells us this tail is always small than 0.12 up to some small exceptional probability. So then the difference certainly is bigger than 0. That's basically the proof. So that's a proof of theorem 1. Conditional, we haven't mentioned the proof of proposition 2 and 3. Okay, that's a general plan. And the proof of the 2 propositions actually, especially the proof of the 3rd proposition, proposition 3 is actually kind of straightforward. We don't do anything fancy. So we want to understand something like the tail of this quantity, and we believe this this contribution of this thing is very small. What we can do is just something called moment method. We compute the high moment of this guy, and then we apply something like Markov type inequality. So basically, if we can understand the 2 case moments of this tail, and then this probability of this tail bigger than any delta will be smaller than the 2 case moment divided by delta to the 2k. Okay. So then this first step will already tell us like something like for each truncation x, any fixed x, the exceptional probability is very small. And now a good thing about this upbound is that it decays very fast with x. Okay, so then we want to show that the tail is always small, not for any single x, but for all larger x. Large means larger than n0. So what do we do? Just simply take a union bounds. We don't do anything clever here. We just take a union bounds that for each one is small and it decays very rapidly. So union bound is also fine. And that gives you a reasonably good control on the exceptional probability such that the tail is small. Is the exceptional probability that tail is large. So that's a plan for proof of proposition 3. And then, of course, because we consider this, we are very careful about this numerical value. So all these steps you should be very careful about. It's like at the end, it's more like optimization. How large you should choose your k, how large you choose your data. It's like optimization after all the setup. We'll see this at the end. So that's a proof of proposition 3. Okay, so now we focus on the proof of more involved proposition is a proposition 2. So we are interested in this Euler product. We want to show that this Euler product at least taking some reasonably large value. It's not extremely close to 0. And we want it to be positive and not extremely close to 0. So if as long as the truncation x is large enough. Okay, that's our plan. And the proof is, again, roughly first for any fixed x, by using our moment method, roughly speaking, we can show that this truncation point of up to x, this is a random Euler product, such that it's smaller than delta will be very small. Okay, this is not precisely, rigorously, this is not correct. There's probably some constant c instead of 1, but I just give you a roughly a feeling like how this bound looks like. So it's like decay in this speed. So you can see that if you take delta to be very small, then this quantity will be very large, then take exponential negative. So this will be decay very fast. So again, here we didn't use anything fancy. Again, it's just like you want to understand this structure. So you're using moment method, you compute these large moments. And but the key point here is like the right-hand side. If you look at the right-hand side, if you still remember the statement of the proposition, we finally the numerical value we pick for delta is something around this 0.1 or something. So this guy is actually just a constant. It's a very small constant, but it's a constant. So this right-hand side above now is a small constant, and then this is only for a single fixed x. So that means like you cannot simply take a union bound because, well, there are infinite number of x you need to worry about simultaneously, and the right-hand side for each of them is a fixed constant. So if you take union bound, the system will blow up. So here it's different from the case for large x. We can take union bound because we have the exception probability somehow decay rapidly with x, but here it's slightly different. So we cannot take union bound. We cannot do the trivial thing. But it's not too bad. What we do is like, first, at least this is true for x equal to n0. That means your random Euler product up to n0 will be reasonably large, larger than delta, up to some very small probability, exceptional probability. So it's like we first apply our result in step 1 for x equal to n0, and then as long as we can show that all the rest from product from x to any point you stop at x plus y, let's say, this contribution actually is very small. It's like you don't need to worry about it. This product is always very, 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 very close to 1. That is, as long as if you stop at n0 is big enough, then it will always stay big. So it's always like after n0, it doesn't change too much. That's basically the plan. If you can show this inequality, like understand this probability, if we can control this probability, that is, okay, in more probabilistic language, you can consider like it's like a random walk. You stop at n0 and you achieve a reasonably large value, let's say 0.1 or 0.2. And then what do you want to show that from n0 to all the rest, it will roughly stay at the same place. Like the value doesn't change too much. That's basically this inequality this probability is talking about. Like the rest product is very close to 1. Basically they don't contribute too much for all infimum. Here we have an infimum y for all y. So it's like for all the steps later. So how to prove some inequality like this? And there's the key here is now we are in the situation of this random Euler product, and all the FP are independent. So if you take a logarithmic of this product, it's roughly just sum of some, it's just roughly some sum of not RID, but at least independent random variables. And we can have good understanding and many standard tools in probability to deal with this kind of thing. So that's, if you're familiar, that's usually people call it a maximum type inequality. So the remaining goal is just establish this inequality and this standard application of some maximum inequality. And the inequality we want to use is called arithmetic inequality, and it's basically say, if you look at this statement, it's like if you have sum of independent random variables, and then you can control the maximum of this sk for any k in certain range by the single one. And so the up bound is, this inequality really tells you that it can pull out the maximum inside the probability. Usually it's a harder one to bound it, the up bounded by something like a right hand side. So you pull out the max, and this infimum in our problem is just exactly corresponding to this max here. So that's how you can get a good bound on this exceptional probability. And it just reminds you that okay, why we choose this inequality? There are a lot of other inequality similar flavor like Kolmogorov inequality, but I guess for us we really care about the numerical value, so we care all this kind of constant stuff. So it's really optimization problem. So I give some quick conclusion remarks. So the first proof, the proof of theorem 1, I hide in a lot of details, but the roughly structure is like you, after all the main idea I just mentioned, it will become an optimization problem, and you want to plug into some Python and can compute them, and then with a very careful choice of parameters, and then you will be able to achieve the result we just claimed. And I didn't mention the proof of theorem 2, but as you can see from our paper, I just say the statement, actually theorem 2 just follow very directly from theorem 1, but we have a lot of advantage now because we don't really care about anything like small value of x. We also, we don't care any multiplicative coefficients, so we can always use a lot of big O, and most of the places, so it's actually simplified the proof a lot. So theorem 2 is really easy of follow-up of theorem 1. Okay, I think I stop here.
Thank you very much. Do we have any questions for our speaker? Maybe from the probabilists in the audience?
Yeah, I just have a quick question now.
Yes.
Louis Pierre speaking. Okay, thanks, Max. Very nice results. I was just wondering if you can get more information about the distribution of that sum. So your result is that it's bigger than 0 for all x. Maybe you can look at the distribution. Yeah, how is it distributed for all x as x varies? I'm not sure what the question is.
Yeah, thank you for Louis Pierre. Yeah, that's a very nice question. So actually, we also consider a bit. It seems not that easy, but it's certainly a very interesting question we want to understand. Yeah.
Yeah, it's probably hard, but I'm just wondering how much you can push it through. Thanks.
Yeah, I definitely agree. For even like the tail, the term about the tail, like we know the tail is small, but even for those tails, you can consider the distribution of the original sum, or even you can consider the distribution of the tail. None of them we understand it yet. So yeah, but it's a very nice question. Yeah, thank you.
All right, thank you.
Other questions for our speaker? If not, then I thank Max again. Our next talk will be in